Hello guys, welcome to AP Stats with Warnke. I'm excited to tackle the challenge of AP Stats with you today. So these are the learning targets we're going to be covering today. We're going to be talking about three different things. We're going to be talking about percentiles. We're going to use percentiles and then get into our cumulative relative frequency graphs. Those are something that are you can use on the AP exam, but is not something that's specifically going to be on the AP exam. And then lastly, we're going to talk about standardized scores or z-scores. So that is a huge idea. That's a principle that we're going to be using just about every single day in AP stats from here on out. Z-scores are how we describe data, how we use to kind of compare a lot of things. And it's how we take information that is not necessarily nice, we can make it a lot nicer, a lot easier to work with. So here is our first definition. It's about percentiles. So we can look at the definition as you kind of copy that down into your notes. And one phrase that should stick out to you is the percent of observations less than it. So that's really what we talk about when we're talking about percentiles. Where is something relative to everything else? How many things are below it? So this is an example that I've kind of put together for this lesson. We're going to be referring back to it at different points. So I'll kind of re-mention this, but this is a stem plot, and with that stem plot, we have a kind of context around that. So Jenny earned a score of 86 on her test. So we can tell about the stem plot that's talking about test scores, and you can kind of see the one that's bolded, right, as you transition from red to black. That's Jenny's score. So how did she perform relative to the rest of her class? So using that definition of percentile, we want to know how many scored less than her. So if we count those up, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 that are below her. She's the 22nd score. And if we continue counting, we see that there are 25 total students. So 21 out of 25 scored below her. So pulling out the calculator, 21 out of 25, and we get 0.84. So she is in the 84th percentile, or at the 84th percentile. So that gives us a little bit of information of where she is. One thing to note is that this number worked out pretty nicely, but percentiles are always whole numbers. So as we look at different things, you're going to get some decimals. You can kind of round those. You can either round it up or truncate it, and then use that number for where are they. So this is an example in your notes. I'm going to keep going on, but if you want to pause it here, look through these, kind of answer these problems at your own pace, and then move on to the next, then you can do that. So we have the Minnesota Twins, who won 66 games, Washington Nationals, who won 98 games, and the Texas Rangers and Baltimore Orioles, who both won 93 games. We want to find those percentiles. So looking at the Minnesota Twins, who won 66 games, they are in the 10th percentile because 3 of the 10s had fewer wins than they did. So again, we have the original question. We can basically take that original question and reword it with our answer. So our answer is the 10th percentile. That's really all you need. So we have the Washington Nationals with 98 games. They're in the 97th percentile because they scored the most. So all the teams below them, 30 total teams, that'd be 29. Notice that that's not the 100th percentile. So even if you're at the very top, you're still at most going to be in the 99th percentile. So that's kind of something to be aware of. And then lastly, 2 teams with 93 wins, the Texas Rangers and the Baltimore Orioles, are at the 73rd percentile because we're only looking at teams who scored below them. So that would be 22 of the 30 teams. So as you're writing this down, make sure to include the team name and the percentile that they were in. You don't necessarily have to include that explanation for because, but you should have that same idea. So the other idea we're going to be talking about today that's kind of a little new, or we're going to build upon that with the percentiles, that's a cumulative relative frequency graph. So that displays the cumulative relative frequency of each class of frequency distribution. So all those words kind of build together. Cumulative, we're going to be adding stuff together. and relative frequency, we're going to be adding things together, those percentiles, to get an idea of where something is relative to the next thing. So in our notes, we have the example of the state median household incomes. The table and cumulative relative frequency graph below, I have it on the next slide, is for 50 states and District of Columbia median household incomes. Here it is. So as we look at this, you can see the frequency. Frequency is how many are in that specific block. So we have from $35,000 to up to $40,000, but not including 40,000. There's only one state in that range. There are 10 states in that next bracket from 40 up to $45,000. From 45 up to 50, we have 14 states. From 50 to 55, we have 12 states. So going over to the next column, we want the relative frequency. So we take that number and then we divide by the total. So 50 states plus the District of Columbia gives us 51. So we take 1 out of 51, 10 out of 51, 14 out of 51, etc. What we can do with those is then just kind of stack them on top of each other. So to get this 11, we took that there was one state below it and then 10 states in that category. We add those together and we get the 11. Then we add on the next 14 states in that next category from 45,000 to 50,000. So if we add those on, it gives us a total of 25 states. Then we can add on the next block and so on and so forth, until we get all the way to our last one, which is 100%. So these are the cumulative relative frequencies. It's taking that cumulative frequency and again dividing by 51. So we take 1 out of 51, 11 out of 51, 25 out of 51. So that graph looks a little bit like this. You notice on the next page we have a few questions. Again, feel free to pause here. I'm going to work through a couple of these, so if you feel like you kind of get what's going on, you can kind of advance ahead, but I want to talk through them. So that first question, part A, says, what does the point at 50, 0.49 mean? So if we look on this, we can find our x-axis is 50. And kind of tracing that up, you can see, all right, yeah, that looks like it's about right at that mark right there. That's about 50% or 0.5. So 0.49, that seems completely reasonable. That's how we're reading our graph. So what does that mean? Well, our x-axis is the median household income. So that's 50,000. And then that 0.49 is our cumulative relative frequency. So using the context, we come up with that the median household income of 50,000 for any state that might have that would put them at the 49th percentile. So here that is. 49% of states had a median household income less than 50,000. For that second part, the 0.55 and 0.725, that means that 72.5% of states had a median household income less than $55,000. Notice that those are less than statements. Those aren't less than or equal to, those are less than. For C and D, what percent of states had a median household incomes between 50 and 55,000? So if we look at our graph, we can look at, okay, what is really the steepness there? So the steeper the graph gets, that's more states we're adding in there. So we want to know what percent of states had incomes between those. So what we can do is kind of trace that up vertically and over horizontally. So for 50, we had 0.49, and for 55, we had 0.725. So we can subtract those from each other, 0.725 minus 0.49, and we get our answer. That's about 23.5% of the states had a median household income between 50 and 55,000. So we subtracted those, and that gave us that cumulative relative frequency. So due to some rounding, there might be little differences here, but that's kind of something to be aware of. We can just use this to get an idea of what percent of states scored at or below a specific number, or scored kind of above a specific number. For those last two questions, again, we're just reading the x and y axes. So as we answer part D and E, at what percentile is California with a median household income of 57,445? We can look along this and try to figure out where that is. So 57,445 is going to be right about here, right between our 55,000 and our 60,000. So tracing up, you get an idea, it's right about here. So, and then trace over, and that's where this comes into play. So I kind of drew a couple lines there, and that definitely looks like it's a little less than 80s. So let's go with the 78th percentile. If it was a little closer, I might call it 79, but we'll go California is in the 78th percentile. To figure out where that first quartile is, remember quartiles are 25%, so we can find on our y-axis where would 25% be? So we have that little notch for 30% or 0.3. We have that little notch for 0.2. So halfway in between each of those, we can draw a line going over and then down. And we get about 45,000. So about 25% of states have a median income less than 45,000. That's our cumulative relative frequency graph. These aren't something that are going to be on the AP test, but something you can use on the AP test. So going back to Jenny, our example from the beginning, we had that she got an 86. And in this case, they tell you that she was 6 points above the mean. What we really want to know is, in context, where does that locate her? Is that good? Is that really good? So we can kind of use a standardized score, a z-score, to help us figure that out. This is a really powerful idea. We're going to start to develop it this section, but we can take any distribution and figure out how does that compare within its own range, within its own context, by comparing it to the mean and then using standard deviation as well to develop that idea. So we need to measure the spread and where is that center. So here is the definition of z-score. You can copy this down into your notes wherever there are kind of some missing spaces, but I'm going to go through that in a little bit of detail. It indicates how many standard deviations an element is from the mean and in what direction. So two things. Number one, how far is it? Number two, what direction is it? Just by looking at that one answer, that one number, it gives you an idea of magnitude and direction. We have our formula, and that's a little bit down below. It is z equals x, where x is the number that we are interested in. It could be, in this case, Jenny's score. It could be anything. And then we subtract the mean and divide by the standard deviation. That score gives us an idea relative to the rest of this distribution. How good is that? And then we have it in symbols. These symbols, we'll get into that a little bit later, but when we have mu and sigma, those represent kind of some population variables. There's a couple assumptions that go along when we use those. For right now, we're just kind of stick with mean and standard deviation, the words themselves. You might also see x bar and then s sub x for mean and standard deviation. Whenever we use the normal Arabic things, we're talking about a sample. Whenever we switch over to the Greek letters, that's when we indicate that we are talking about a population or making some assumptions about our population. So a z-score is often called a standardized score. You might hear about standardized tests or something along those lines. That's something that we can kind of use interchangeably in stats. So let's dig into this example. We know Jenny got an 86, and we know that the class mean was an 80 because she scored 6 above that. So the last piece of information you need to get a z-score is what was the standard deviation. So here it's provided for us that that standard deviation was 6.07. So we can use that to calculate her z-score. We take the number we're interested in, that 86, and subtract the mean. All of that gets divided by the standard deviation, and we get 0.99. So a couple things. A z-score does not have the same units as the original variable. So we were originally talking about points or her score on the test. The z-score, that 0.99, it doesn't have any units on it. It is a z-score. because of the kind of the way we set it up. Our standard deviation was points, and our numbers on top, our numerator is points. So kind of using some dimensional analysis ideas, points cancel out. Last thing is positive means it's above. So if she scored above the mean, we knew that because she got an 86. But if you just see a z-score, you can then indicate, okay, I know where this is located relative to other things. And a negative is going to tell us that that would be below average or below the mean. So we'll do a little bit more with that 0.99. This is where we introduce one of sections of our formula sheet, our AP formula sheet, that'll become in handy. This is another little bit of practice with z-scores. So when comparing z-scores from different distributions, it is important that the distributions are roughly the same shape. If you have something that's skewed left and something that's skewed right, you might end up with some very weird z-scores and relative to each other, trying to compare those two different distributions. So when they're the same shape, that's when you can kind of make an apples to apples comparison. And the more skewed something is, the more common you might get a really large z-score. In this case, Jenny's z-score of about 1, that's not too big. But if you start to see some z-scores of about 4 or 5, that tells you that this could potentially be a non-normal distribution, non-approximately symmetric distribution. We haven't quite introduced normal yet, but that's an idea we'll get to also this chapter. On the same day, Jenny took a chemistry test. So we're back talking about Jenny. We have one more example for you. And on this test, she earned an 82. The class distribution was approximately symmetric with a mean of 86 and a standard deviation of 4. On which test did Jenny perform better to the relative class? Well, we need to calculate the z-score. We can compare z-scores one to another to get an idea of how do they compare. And if you think back to the original distribution of those math scores, that was approximately symmetric. So it's okay to use this distribution because it's, again, also approximately symmetric. So let's take a look at the answer. So remember back to that math problem, we had a z-score of 0.99. Here on the chemistry test, we have a z-score of 1.5. So even though she scored higher on the math test, more points, she actually did better relative to her peers on the chemistry test. That z-score of 1.5 is what tells us that. So Jenny scored better on her chemistry test relative to her peers than she did on her math test. Always include that context. Here are a couple problems in the note packet for you to go over. Feel free to pause the video, work these out on your own, and then check your answers. So we have the Yankees were 1.18 standard deviations above the mean, and then the Mets were 0.59 standard deviations below the mean. So again, we have that negative z-score that indicates that they were below the mean and how far, and the Yankees were above the mean and by how far. So they were kind of well above the mean, one away, whereas the Mets were kind of mediocre below the mean. Not super far below, only about 0.6 of a standard deviation. It is okay to round these to about 2 decimal places. That would be the preferred one because when we use our tables in the AP formula sheet, that's what they have is 2 decimal places. For the last problem in the note packet, here is that table. So we have 4 players. They all hit a lot of home runs. They all broke the home run record. But comparatively speaking, which one had the best season? So as you notice, we have 60, 61, 70, and 73 home runs. So the number is obviously increasing. But so is the mean for all of baseball. That mean column represents all of baseball's mean home runs. So we had 7.8, 7.2, 18.8, 20.7, and 21.4. And also, you kind of notice that the standard deviation tends to increase. So it kind of leveled off there, but increasing in general. As we look at these, maybe you get a little bit of intuition from what we've been doing so far as to which one of these might be the highest. Take a moment, calculate the z-scores on your paper. Once you've done that, you'll have the answer, obviously, but compare it to what we have. So from all of those, we have that Babe Ruth had the highest Z-score of 5.44. That's a huge Z-score. Obviously, all of these are pretty big. Seeing a Z-score around 4 or even around 3 is very big. These guys all had fantastic seasons, much better than everyone else in the league. But comparatively speaking, Babe Ruth did amazing. That 5.44 is just a very substantial Z-score. So he is still a home run champion. We're talking relative to the rest of his division. That's all I have for you today, guys. Thank you for joining me for AP Stats. Feel free to let me know if you have any questions in class tomorrow. And I look forward to taking on the challenge of AP Stats with you next time.